right? And that acceleration, we put it equal to dv by dt, and then we change it to in the form of x. So this was dv v dv by dx, right? So acceleration was v dv by dx, right? And then we calculated, to calculate velocity, we integrated both the sides. That's how we got the velocity. Right, this was the idea of this question. There is another idea, right? I didn't talk about in the previous class. There is another idea that we can do this problem whenever you want to calculate velocity. Whenever in the question it has been asked that you have to calculate velocity, then there are different forms of the forces and all those things, right? So one idea would always be there, and that is work energy theory. Right, so this will always be there. So in this question, you can write that change in kinetic energy, that would be equal to change in potential energy. Right. So in a conservative of force, we can write the change in kinetic energy equal to work done, and work done is change in potential energy. So because this is a conservative force, because force is directly proportional to 1 over some x. So this is a conservative force, so we can write or x square, whatever. Force is some function of x. So this is a conservative force, and we can write this thing, right? Clear?
Yes, sir.
Okay, so now we were talking about the next part, which was electric dipole and the torque. So we have this electric dipole and the torque experienced by this electric dipole. Right, this is the last question that we did. And now we were talking about, so now we were talking about torque experienced by electric dipole in an external electric field. Derivation we will not do because that part we have already done, right? So we have electric field. This is a uniform electric field, right? So I should write uniform. So we have a uniform electric field, and then we have a dipole, right? We have a dipole, which is something like we have this type. Right, this is minus q, this is q. So what would be the direction of the dipole? What is the direction of the dipole? From where to where? Yeah, from where to where there would be direction of the dipole movement. What is the direction of the dipole movement? Yes, Rishita. This thing you have done, right? You have completed the first step, right?
Yes, sir.
So what is the direction of the dipole moment? This was a very this.
From negative to positive.
Yes, absolutely right. So why were you hesitant, right? So this is the direction of the dipole, right? Absolutely correct. So this is the direction of the dipole moment. So you see that this dipole moment is making an angle theta with this electric field. So direction of the electric field is this. Right? This is the electric. So this is electric field, this is dipole moment, and we will have some force experienced by these two charges, right? So this positive charge will experience the force in which direction, right or left? What would be the direction of the force experienced by this thing? Left or right?
Right?
Right, because this is a positive charge. So this is F, which is QE. Right, this will experience a force in the left direction, which is F, and this is minus QE. So what do we have? We have a net force. I should use a different color, right? So we have a net force. This is F, which is QE. And this is again F, which is minus Q. So you see that the magnitude of these forces are equal, but they are in opposite directions. So F net is how much? How much is F net?
Positive QE.
So that would be QE plus minus QE. F1 plus F2, that is the F net, right? There are two forces.
Yes,
So
sir.
the F net would be just the addition of these two. So this is QE and then minus of QE. So this is 0, right? So there would be no translation motion. So this is translational equilibrium, right?
Yes, sir.
But this is creating what? A couple, right? So this is the line of action, and this is the line of action, and we have a net couple. So this is creating a couple. This is creating a torque in this direction. This is creating a torque in this direction. So we have a net torque, right? And this will have, so we don't have any rotational equilibrium, right? So this will rotate. This will rotate this dipole. Because we don't have any rotational equilibrium, right? So we will have a net torque, which is P cross E. This thing we have derived, so I will not write, because this thing we have already done, right? And what is the magnitude of this thing? This is PE sine theta, right? And there are three cases. One is the stable equilibrium, unstable equilibrium, and then we have maximum torque. All those positions, right? Those things we have done already, right?
Yes, sir.
Yeah. So please note down all these things, because these are the only things that we will require, right? These are the only things we will require. And yeah, we don't need what is the unstable equilibrium, what is the stable equilibrium, and what is the maximum torque. So I can write those conditions, right? So let me just write those conditions as well. So three conditions is the stable equilibrium. And this is rotational equilibrium I'm talking about, right? What is the stable equilibrium? For what? Theta equals to how much?
0 degree.
0 degree. Absolutely correct. Good. And we have unstable equilibrium.
180 degree.
This is 180 degree. And then we have maximum torque. This is
90 degree.
Yeah. So these are the special three conditions, right? And to pictorially understand, right, what is the stable equilibrium? So if I have this thing, right? So this point, and let's say if I have this thing. So there are two positions. This is let's say these are two curves, right? And you have a spherical ball in these two positions. So if I move this thing in this direction, if I move this thing in this direction, so which will come at its original position? Which will come? The first one or the second one?
The first one.
So if I move this bead, this will go down, right? Will it come back to its initial position?
Oh no, no, you said no.
Right? Yeah. If I move this thing in here, it will always come down. It will go here, oscillate, and then it will come down. Right? So it will come back to its initial position. It will come back to its initial position. So that is why we call it stable equilibrium, right? Both are balanced. If you put this bead at this position, if you're not doing anything, so this will remain at this point, right? And this will also remain at this point, but they are two different kinds of equilibrium. This is stable because it will come back to its initial position. And this one is unstable. It will not come back. So this is unstable equilibrium. We understand the idea of stable and unstable. Yes.
Yes, sir.
Then please note down this thing and then we will do some questions. So I have only collected one question, but yeah, I will also do other questions. Actually, there are lots of questions in dipole and top. But there were some different kinds of questions. These are not necessary, but the important ones I will do yeah, at some later point. But yeah, we will do one question from this. Please note it down. And whenever you have noted, please tell. You have noted it down, please tell. Yeah, whenever you have no to equals to. Yes, whenever you have no to please tell me.
One second, sir.
Yeah, yeah.
Done, sir.
Done. Okay, so we have one question, right? To use this idea, let us do that question, and then it will clear the doubts, right? So, yeah, so we have this question. An electric dipole has a fixed dipole moment P, which makes angle theta with respect to x axis, right? So let's say we have these axes. Oh, this one is and this one. So this is x. This is one. Right. Now we have an electric dipole. Let's say this one, and this is making an angle theta with the x-axis. Right. Now we have two cases. In one case, we have when subjected to an electric field E1. So what is the direction of the electric field, this E1? What is the direction? Can you tell me? Yeah. What is the direction? Yes.
Z direction, K cap direction.
Where is key? Where is key? Direction of electric field, I'm asking.
Negative to positive, negative.
So this is I hat only, right?
Yes, sir.
So this would be x-axis, right?
Yes, sir.
So direction of E1 is this one. This is E1, right? Magnitude is E. That is the magnitude is E. Now you have the second case. In the second case, it is subjected to another electric field E2, which is √3 magnitude of E1 and J hat. So what is the direction of the electric field in this case? What is the direction of E2?
J cap.
X, Y, Z.
Y.
Yeah. Y. So this is E2. Right. So this is E2. Now, can you tell me that what is the angle the dipole is making with E2?
90 degree.
90 degree.
90 minus theta.
90 minus theta, right? So this is 90 minus theta. Absolutely correct. Right. So this is the dipole that we have. Now we can write first case. Case first. What is the torque that we have? Tau1. And they are writing it as T1. So let's write it as T1. Right. This would be P cross E1. Am I correct?
Yes, sir.
So magnitude, let's suppose that magnitude of P is P. And then magnitude of E1 is E. Right. So this is E. And then sine theta. Right. And the direction they have said that this is K. So the magnitude of T1, which is tau, right? Magnitude of T1, which is tau. This is P, let me write it as tau1. This is PE sine theta. Is it correct?
Yes.
Now we have second case. So now we have second case. In this new case, we have the top, and this is equal to P cross E2. Right. So this would be magnitude of P, magnitude of E2, and then sine of the angle. What is the angle that we have between P and E2? Yes. What is the angle between
90
P?
minus theta.
90 minus 3. So this would be 90 minus 3. Correct. Clear. So this would be PE2. And what is sine 90 minus theta? That is a complementary angle. What is sine 90 minus theta?
Cos 90.
Cos theta. Cos theta. Right.
Yes, sir. Cos theta.
So this is, and we have not written the direction but in here they have already told that this is T2 is minus of T1. So direction is opposite. So this is, let me write only, this is minus of K. Right. So this is minus of K. Because if I'm writing T2 is minus of T1, which means that both the magnitudes are same, but the direction is opposite, right? If these two vectors are equal, right? If these two vectors are equal, then their direction and their magnitude should be equal. But this is minus T1, which means that these are in the opposite direction, right? T1 and
Yes, sir.
T2 are in opposite direction because we have T2 vector, this is minus T1 vector, right? And because these two things are equal, so this is first information. Second information is that magnitude of T2, that is equal to T1, right? These 2 points are clear. Are these 2 points clear to you with this information?
Yes, sir.
So this is P, and what is the magnitude of E2? That is root 3 E1 magnitude. So that is root 3 E. And cos theta minus A. So if I write the magnitude of T2, that is tau 2. So this is simply P root 3 E cos theta. Is it clear?
Yes.
So it is given, right? It is given that magnitude of T1, this is equal to T2. So what is the magnitude of T1? That is PE sine theta. And then what is the magnitude of T2? That is P root 3 E and cos theta. So E and E cancel, P and P cancel. And in the question, we have to find the angle theta. Right? What is this angle theta? So that is what we have to find. Right? So let us solve this further. So this is sine theta, cos theta will come in the left hand side. This is root 3. So we have tan theta, which is root 3. So what would be theta? For what value of tan we have root 3? What would be theta?
60.
60. Right? So that is your answer. So this is the answer, right? Is this question clear to you? Yeah, is
Yes,
this
sir.
then please note it down. Then we'll do the next topic, right? So there are other questions as well. I have not written in here, but I will do those questions in the later half, right? So at some later. There are other questions. There were other questions that were quite lots of questions. Yeah, we will do this question later, but yeah, just one question to understand this. Whenever you have look at this, Yeah, whenever we have please take. Yeah, whenever you have please take.
Done.
Yeah. Okay. So now let us understand the next topic, which is electric flux. Right. So yeah, I will write it in here. I will use this thing in here, but I will write it. Okay, so what is an electric flux?
Electric current from the one terminal to the other.
Electric current from one terminal to the other. That is current only, right? So we are doing the first chapter. In the first chapter, we don't have any current, right? Why don't we have any current in the first chapter?
Electrostatic, sir.
Yeah, electrostatic, because charges are at rest, right? So we don't have any charges moving. So electric flux is the number of electric field lines passing normally through the surface, right? So if we have the surface and these are the electric field lines, so the number of electric field lines, let's say 1, 2, 3, 4, 5. So electric flux would be 5, right? And this is numerically defined as E dot A, which is EA cos theta. So this is the electric flux, right? Right?
Yes, sir.
And we have a Gauss law, which is very important to understand the electric flux, right? So what does this Gauss law states? Gauss law of electric flux. What does it say? So it says that in a closed loop, right? In a closed loop, if you calculate the flux in a closed loop, right? And this should be, yeah. So let's say in a closed loop, let's say this is some charge Q. If you calculate the flux, then this flux is equal to Q enclosed by epsilon. That is the Gauss law, right? And this flux in the closed
Yes,
loop is defined as E dot ds and this closed loop, this loop has to be closed. Right, this is what we call the Gauss. These things you have done already, so I will not elaborate these things. I will just write it down, right? Because of this curved surface or because of this closed loop, we have this Gaussian surface, right? So by using the Gaussian surface, we can write this closed loop as simply EDS. Right, so Gaussian surface is one such surface in which this E dot ds, the angle between electric field and this thing is either 0 or 90. If it is 90, then this thing would be 0. If it is 0, then this would be simply EDS, right? Because E dot ds is EDS cos theta. And we take the Gaussian surface in such a way that for Gaussian surface, this theta is either 0 or 90. Right, so then this simplifies this thing. And it simplifies to this, that is how they use for this Gaussian surfaces, right? So these things you have already understood, right? Right,
Yes, sir.
yeah, and using this Gaussian surface, using this Gauss law, you have derived. So using this Gauss law, you have derived the electric field of infinite wire, right? And you have this infinite wire. This has some charge density, and this is infinite. You take this Gaussian surface, and then you calculate this electric field at this point. Then it comes out to be, so this electric field is simply lambda by 2 pi epsilon naught r with this r, right? This thing you have already done, right? And then the another use of this thing is electric field of sheet. Right, so how do we calculate the electric field of sheet? So we have this sheet, right? And then this has some charge density. So we take some, again, some Gaussian surface, right? Again, we take some Gaussian surface. And then we calculate this electric field. So using this Gaussian surface, we calculate this electric field to be how much? What is the electric field of this sheet?
Um,
So this is a sheet. So it will have surface charge density, right? So this is sigma by 2 epsilon. I'm not writing the derivation. That thing you have already done, right? So this
yes.
sheet, so there would be two kinds of cases. Right, let's say if you have this positive sheet. So for this positive sheet, there would be electric field in this direction. In the right hand side, in the left hand side, electric field is in this direction. Right. So this is, let's say, E1, which is sigma by 2 epsilon naught r hat. And this would be E2. This is sigma by 2 epsilon naught minus r. Right. So the electric field would be in different direction, in right hand and in left hand side. Right. If I have a negative sheet, so if I have a negative sheet, then the electric field would be income. But this would be, so then this E2 would be sigma by 2 epsilon naught r hat, and this E1 would be sigma by 2 epsilon naught minus r. So these things would be important when you understand capacitor, right? When we would be doing capacitor, so these things would be important. Clear up to this point?
Yes.
Okay, then yeah, so the next topic, which is very important, so this is very important, and this is the difference between the electric or between the sheet and plate, right? Or I should write conducting plate. So sheet has this thin shape, but conducting plate is of this kind, right? So it has this side, it has two sides, right? So this is a conducting plate, and this is a sheet. In the sheet, the charges are distributed uniformly, right? But how are the charges distributed in conducting plate, right? So let's say this would be some charge, and this would be some other charge. But inside there would be no charge, right? Let's say this is there is some inside thing, right? So there would be no charge inside this conducting plate. So this conducting plate will have these three regions, right? One would be inside region, then these two other outside regions. So you do understand this part?
Yes, sir.
Okay, so yeah, note up to this point, and then we'll do the question based on this thing. How will the charge will be distributed of this conducting plate? So these are the question that we will do. Please note down these things. Please note it down, and then these are the question that we will be doing. People need to. Okay, yeah. So these are the things that you have already done, right? So I just recapped this thing. Please note it down, and then we will do other questions, right? Whenever you want me to scroll down, please tell. For disconnect. And yeah, you keep revising, Rishita, right? Otherwise, you will forget. So please keep revising all these things.
Yes, sir.
But whenever you want me to scroll down, please tell me.
So can you scroll down?
Scroll down.
Yes, scroll up.
Up, so there's nothing there, right?
Yes, scroll down, sir.
So, yeah, up to this point, we have noted, so no down for me. Right, so this is the topic that we will be covering in the next set of class. So let's say I give you these plates, conducting plates, and I give you, let's say, this one contains 3Q charge, this one contains 4Q charge. So what would be the distribution this side? 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 So that is the kind of question that we will, right? Because for conducting plates, the distribution can be different, not like the sheets, right? Sheet has only one shape, so this doesn't have any inside and all these regions, right? So sheet has only two sides, this one and this one, and from both the sides, the distribution would be same. But for conducting plates, the distribution can be different. So that is the difference we would be talking about, right? Yeah, please note it down, and then if we get time, then we'll do one question or we'll stop. Yeah, whenever you have noted, please.
Done.
Done. Okay, so yeah, the next question. What is the next question that we would be doing? So the next question is that, let's say that I have this plate. This is not a sheet, right? This is a conducting plate, and I have this Q charge, right? This is plus Q charge. So what is the distribution would be there in this side, and what would be the distribution there in this side? That is the question. But in this conducting plate, one key point we have to always remember that inside the conducting plate, electric field is zero, right? Or I should write E net is zero. So this is the key point. Point in every class of questions of this conducting. So I will stop here. and from here I will start. Right. I was just